What we're going to do now is develop an equation of a plane in three-dimensional space. What we're going to develop is called the normal equation of a plane, and so it is worth looking back at the normal equation of a line. The normal equation of a line is something like 3x plus 2y equals 12. Why is it called this? Well, look at these components 2 and 3, these coefficients. If you think about the vector 3, 2, the vector 3, 2 is actually perpendicular to this line, and we call this vector a normal vector. This is where the idea of the normal equation came from, is that the coefficients of x and y are given as the coefficients of a vector which is perpendicular or normal to your line. We're going to use the same concept when we talk about a plane. Every plane has a normal vector. It's a vector that's perpendicular to any line that it meets in the plane. In three-dimensional space, every plane has these normal vectors. Of course, a normal vector could be longer or shorter and still be perpendicular to everything in the plane. So there are infinitely many normal vectors, but they're all parallel to each other, though of course some could face in opposite directions. So let's look at an example and see if we can understand how we can use the normal vector to find the equation of a plane. Here's a plane whose normal vector is 3, 1, negative 2, and it contains these 4 points, P0, P1, P2, and P3. What do all of these points have in common? Well, take a look at the vectors in the plane from P0. The vector from P0 to P1, the vector from P0 to P2, and the vector from P0 to P3. All of these vectors are orthogonal to n. They make 90-degree angles with it. And so what that means is that if we were to compute any of these vectors and take the dot product of them with n, we should get 0, because orthogonal vectors have a 0 dot product. Let's just do one of these vectors as an example. So let's take the vector from P0 to P1, which we can get just by subtracting the components. It's 3 minus 1 for the x component. It is 5 minus 5 for the y component. And it is 1 minus negative 2 for the z component. And so we get 2, 0, 3. What happens if we take the dot product of that with n? Well, we get 2, 0, 3 dot 3, 1, negative 2, which is 6 plus 0 minus 6, which is 0, just as we hoped. And so, in fact, for any point on this plane, any point q, I guess, we can write that P0 q, which would be x minus 1, y minus 5, and z minus negative 2, if the point q is x, y, z. And if q lies on this plane, what we better have is that x minus 1, comma, y minus 5, comma, z plus 2, dot product, the normal vector, 3, 1, negative 2, needs to be 0. And in fact, we could actually take this dot product. We get 3 times x minus 1 plus 1 times y minus 5 minus 2 times z plus 2 is the dot product in question. And if x, y, and z lie on the plane, then this dot product needs to be 0. So let's generalize what we just did to get the vector equation of a plane. If r0 is some point on the plane, or some position vector on the plane, and we have a normal vector n whose coordinates are a, b, and c, then the way we can describe the set of points that lies on this plane is by taking the difference of their coordinates, which is the vector between them, that in our diagram over here, if r0 is our initial point, here's our r minus r0 here, which gets us to the point r. and we take the dot product of that with n, and that equals 0. So this is the equation written as a vector equation. If we want to multiply out the components like we did previously, we could take r minus r naught to get x minus x naught, y minus y naught, and z minus z naught. And then we could take the dot product with ABC, and we could get this equation here. And of course, that dot product has to be 0. And this is actually called the normal equation. Either of these are perfectly good equations. If you'd like, you can clean up the normal equation a little bit. Since x naught, y naught, and z naught are just constants, they're the coordinates of your initial point, you can distribute the a to the x naught, the b to the y naught, and the c to the z naught. And you can then collect those into a single term d, which has been done down here. This is also called the normal form. So let's practice using this form a little bit. First, let's find the equation of a plane that goes through 0, 2, 3, 4, 1, 3, and 2, 2, 0. Let's remember what we need. We need a point, and we need a normal vector. Well, we have actually a selection of points here, and it doesn't matter which one we use. We will get a correct equation. So for our point, we could use 0, 2, 3. And that's going to be our x naught, y naught, z naught. For a normal vector, we need something that's going to be perpendicular to every line in the plane. Well, we actually have a way of finding something that's perpendicular to a given maybe pair of vectors, and that's the cross product. We know we can find two vectors in this plane. So here's two vectors in the plane. We can do that by just subtracting the coordinates of these points. So we can have 4, -1, 0. That's between these two. And we could also take the vector, say, between these two. From 0 to 2, we go 2. From 2 to 2, we go 0. And from 3 to 0, we go -3. So here are two vectors in the plane. If we want a normal vector to the plane, well, anything perpendicular to both of these is going to be normal to the plane. So we could derive our normal vector is equal to 4, -1, 0, cross 2, 0, 3. Let's compute this cross product. N equals, we'll write the determinant, I, j, k, 4, -1, 0, 2, 0, 3. And so what is this? This is I times -1, 0, 0, 3 minus j times 4, 0, 2, 3 plus k times 4, -1, 2, 0. This is I times, well, let's write the coefficient in front. This is -3 times I minus 12 times j, -2 times k. So that's the normal vector. Could be flipped around in the other direction and still be normal. We could use the positive version, 3i plus 12j minus 2k. Well, here's our normal vector. We have a normal vector. We have a point. Let's go ahead and plug these into the equation. Our equation will be then 3 times x minus 0 plus 12 times y minus 2. Oops, this was supposed to be a plus. Plus 2 times z minus 3 equals 0. That's completely correct. If we like, we could distribute, and we could get 3x plus 12y plus 2z, and we're going to have a minus 24 and a minus 6, so minus 30 equals 0. Either of these is correct. This example asks us to understand how a line interacts with a plane. Here we have the vector equation of a line, and here we have the normal equation of a plane. The question is where this line meets the plane. Your instinct might be to plug the x, y, and z coordinates of this line, x, y, and z, into the plane and see what t has to be. And your instinct would be correct, because the equation of a plane tells you when a given x, y, and z lies on the plane. In order for the point on this line to also be on the plane, it has to satisfy this equation. So let's go ahead and try this. We would write 3 times 2 plus t plus 1 times 4 minus t minus 2 times 5 equals 4. And now we can solve for t. 6 plus 3t plus 4 minus t minus 10 equals 4. On this side I have 2t plus 10 and minus 10 equals 4. I have t equals 2. Of course, we were asked to find the point, not the value of t, but that's not very hard. We just plug this back in to the equation of the line, and we'll have a point. So our point is going to be 2 plus 2 is 4. 4 minus 2 is 2, and 5 is 5. And that should lie on the plane.